All right, today we are diving into a really beautiful and honestly super clever algorithm that pops up all the time in technical interviews. It's called the Boyer-Moore majority voting algorithm, and it's just a fantastic trick for solving a common problem with some seriously surprising efficiency. So, picture this. You've got a massive list of votes, I'm talking millions, maybe even billions of them, streaming in. Your job is to figure out if any single candidate won an outright majority. But here's the catch. You have to do it using almost no memory. You can't just store a giant list of counts. So, how would you even begin to solve that? Okay, so how do we tackle a problem like that? Well, before we jump into the really clever solution, let's just make sure we're all on the same page about what we're actually looking for. Let's clearly define our goal here. Now, a majority element isn't just the one that appears the most often. It has a very strict definition. It's an element that appears more than half the time. So, if you have a list with 10 items, the majority element has to show up at least 6 times. That greater than 50% rule is absolutely key to this whole thing. The first thing you might think of is, hey, let's just use a hash map or a dictionary to count every single unique item. And yeah, that works. But it means you need memory for every unique vote that comes in. If you've got a massive data stream with millions of different items, that approach just falls apart. It's not going to work. We need something way smarter, way more memory efficient. And this brings us to the core idea behind this algorithm. This really is the aha moment. It's all based on a really simple but incredibly powerful idea: cancellation. Think of it like this. You grab the first element you see and call it your candidate, and you start a counter at 1. Then you just walk through the rest of the list. If you see that same element again, you bump the counter up. If you see a different element, you knock the counter down by 1. And here's the trick. If that counter ever hits 0, you just completely forget your old candidate and pick the very next element you see as your new one. And here's why that works, the crucial insight. If an element is a true majority, that means it has more votes than all of the other elements combined, right? So the other elements simply don't have the numbers to fully cancel it out. They'll run out of votes long before the majority element's count ever hits 0. It's guaranteed to survive this whole cancellation process. Okay, I know that might still feel a little abstract, so let's make it concrete. We're going to walk through an actual example to see this cancellation process play out right in front of us. All right, here's our sample list. We've got 3 1s, 2 2s, and 1 3. To start, we have no candidate, and our count is at 0. Okay, first element we see is a 1. Since our count is 0, that 1 becomes our new candidate, and we set its count to 1. Simple enough. Next up, we hit 2 more 1s. Since they match our candidate, we just increment the count for each one. So we go from 1 to 2, and then all the way up to 3. Right now, our candidate is looking pretty strong. But now things get interesting. We run into 2 2s. Now 2 is different from our candidate 1, so each of those 2s is going to cancel out a vote for 1. The count decrements from 3, down to 2, and then down to 1. And finally, we see the element 3. It's also different, so it cancels out that last remaining vote for our candidate. The count drops to 0, and we've just reached the end of the list. So, what happened? The candidate that was left standing when we got to the end of the list was 1. The algorithm guarantees that if a majority element exists, this survivor is our only suspect. So the final step is just a quick safety check. We do one more pass to actually count the 1s, and we confirm, yep, it appears more than half the time. And in this case, it does. So now that we've seen all that logic play out, you are going to be amazed at how cleanly and just simply this whole idea translates into actual code. Just take a look at this. This little snippet of Python code, that's the entire algorithm. You've got your loop going through each number. See that first if? That's where we pick a new candidate when the count hits 0. The elif handles incrementing when the numbers match, and the else handles decrementing when they don't. It's a perfect one-to-one translation of the logic we just walked through. So elegant. So, okay, the logic is elegant, the code is simple, but why is this algorithm considered so powerful? Why is it such a big deal? Well, let's take a look at its performance. This slide right here tells the whole story. Now, both approaches take linear time, or O of n, which just means they have to look at every element once. No getting around that. But look at the memory difference. It's huge. A frequency map needs space for every single unique element. But Boyer-Moore, it needs O of 1, or constant space. That's the magic. It only ever stores 1 candidate and 1 count. It doesn't matter if the list has 10 items or 10 billion. So let's sum it all up.
The Boyer-Moore algorithm is this hyper-efficient way to find a potential majority element. That constant O of 1 memory usage makes it absolutely perfect for massive data sets. And it all works because of that core, clever insight of just systematically canceling out the non-majority elements and seeing who's left standing.
And that efficiency isn't just some theoretical thing for an interview question. Think about the real world. You could be analyzing a live Twitter stream for a trending hashtag, processing data from millions of IoT sensors, or tallying votes in a massive online poll. In any situation where the data's pouring in and memory is tight, this algorithm is the perfect tool for the job. And that is the Boyer-Moore algorithm in a nutshell. But it leaves us with a really fascinating thought, doesn't it? This whole idea of pairing and canceling opposing items turns out to be a really powerful mental model. So it makes you wonder, what other complex problems, maybe even ones completely outside of programming, could be simplified if we just found a clever way to let things cancel each other out?